All right, so what I want to do is we're leading into, we're going to do what we call constrained optimization, and we're leading into a way that we can use a gradient to help us with optimization problems. So I want to do a couple of examples that have to do with constrained optimization. So let's say we have, we're on a paraboloid, z equals x squared plus y squared. So hopefully everybody, we can see this is a nice paraboloid. And we have a point on the xy plane, 5, 5, 0. And we want the minimum distance from the point to the paraboloid. So what we're looking at, just draw a quick sketch. We have a nice paraboloid here, and we have a point here on the xy plane, and we're trying to figure out, there's some point on the paraboloid where the distance from 5, 5, 0 to the paraboloid is going to be the minimum. And we want to find that point. Anywhere on the paraboloid, we just want to make sure that this distance is minimum. The length of that segment is the minimum. It doesn't necessarily turn out that way. So we're not going to use a gradient today. We'll use a gradient tomorrow. So what are we minimizing here? Distance. So we minimize the distance, is square root of x minus x0 squared, that's our point, plus y minus y0 squared, plus z minus z0 squared. So we have to minimize that thing. Well, what is the problem? The first problem that we see with minimizing that thing. Right, there are 3 variables, right? This is an x, y, and a z. So, and we've only been talking about minimizing 2 variable functions. Well, we have, so we're minimizing the distance, but we're subject to the constraint that z equals x squared plus y squared. So we have a constraint, we call this a constraint. Sometimes it's called a side condition, is that z equals x squared plus y squared. So like we've done in the past, we just did it in pre-calc where we wanted to maximize the area of some kind of rectangular thing, and we had an x and a y, and we knew that the perimeter or the amount of fence that we had was a certain amount. We can substitute from one equation for x or y, and we just get an equation in a single variable, and then we can maximize or minimize that. Usually it's a parabola and we're finding the vertex. Do the same thing here. So what we want to do is minimize, in this case, minimize our distance equals, I'm just going to substitute for my points and for my constraint. X minus 5 squared plus y minus 5 squared plus z minus 0, and z is x squared plus y squared squared. And now we have a 2 variable function that we can minimize. Well, we've seen examples of this in the past a few times. If we want to minimize this radical, what can we do to make our lives easier? So minimize the square of the distance, or minimize the radicand, what's inside here. So make our lives easier. I'm going to call it d equals x minus 5 squared plus y minus 5 squared plus x squared plus y squared squared. So we're minimizing the square of the distance, and that's going to minimize the distance also. All right, so that's what we're going to minimize. So let's take our partial derivatives. We're gonna do our process. We're going to find our critical points. So d sub x. When I do my partial derivative, 2x minus 5 plus 4x times x squared minus x squared plus y squared. And I can write this, and I'm going to write this first part in a slightly different form. 2x minus 10 plus 4x times x squared minus y squared. We get a similar derivative for the partial with respect to y. Plus, thank you. I don't know why I want to keep it minus. Maybe it makes the problem easier if it's minus. We get a similar expression for our derivative with respect to y. I'm just going to write it over here. Equals 2y minus 10 plus 4y x squared plus y squared. All right, so I'm going to switch the page, and I'm going to distribute here. But this is a system of equations. We want these to be 0 simultaneously. All right, so this is going to be an interesting bit of algebra here. So d sub x is 2x minus 10 plus 4x to the third plus 4xy squared, and d sub y is 2y minus 10 plus 4y to the third plus 4x squared y. So we want d sub x equal d sub y equal to 0. So our system of equations becomes 2x plus 4x to the third plus 4xy squared equals 10, and 2y plus 4y to the third plus 4x squared y equals 10. So that's our system of equations. And we need to solve for x and y. I'm going to call this equation 1 and this equation 2. What are we going to do here?
Quit.
Guess the chick. Sean's got a good
Some wild
check.
One works.
Yeah, I'm gonna say
No, one.
0, 0.
Well, here's what I would suggest. Well, we can divide everything by 2, right? Just to simplify things. X plus 2
Obviously.
x to the third plus 2x y squared equals 5. Y plus 2y to the third plus 2x squared y equals 5. What if we multiply one by y, multiply 2 by x? When I do that, I get xy plus 2x to the third y plus 2xy to the third equals 5y. And when I multiply the second one, I get xy. Oh, that looks nice. Plus 2xy to the third. Plus 2x to the third y equals 5x. Well, what can I do now? I have an xy here. I have a 2x third y, a 2x third y, a 2xy cubed, 2xy cubed. How about subtract those two? subtract, and I get 5y minus 5x equals 0. And so y equals x. That's nice, right? We know y equals x. Substitute into one or the other of the equations. I chose substitute into 1. I substituted into 1. And I get x plus 3x squared plus 2x cubed this should be a, is that right? This should be a 2x cubed plus 2x cubed equals 5. There we go. There are two 2x cubes. So x plus 4x cubed equals 5. That's the equation we need to solve. This is the one I'm going to factor, but I'm going to do one thing first. X plus 4x cubed minus 5 equals 0. So if this were a more complicated equation, this would be the equation we needed to solve. So I just want to do one thing here. Think way back, Descartes' rule of signs.
What? Yeah.
We have one sign change. So that tells us we have 1 positive 0. If I substitute negative x in here, I have 0 sign changes. So that tells us there are no negative real zeros. So I have 1 real 0. Well, let's factor this. X times 1 plus 4x squared equals 5. I'm going to factor that one. Now, some of us saw this one before. We can say by inspection, x equals 1. Right? If I substitute x equals 1 in here, 4 plus 1 is 5 times 1 is 5. Otherwise, if this were a more complicated polynomial, you'd have to remember you do your p's and your q's and you do synthetic division, that kind of thing. All of that stuff that all that great algebra that we learned in pre-calc.
I know, I was trying to think, sorry, how many?
By inspection, x equals 1. So y equals 1. So y equals 1. And we substitute into z equals x squared plus y squared. Z equals 2. And were we trying to find our point? What were we trying to find? We were trying to find the distance. So our distance, I'm going to go up here. So our distance equals the square root of 1 minus 5 squared plus 1 minus 5 squared plus 0 minus 2 squared. And our minimum distance turns out to be 6 units.
Wouldn't it be 2 minus 0?
Doesn't matter, Dylan, you squared it.
Yeah, but it does matter because it's an equation.
Oh my god.
Okay, sure. I'll turn it around.
Oh, Dylan, I was literally about to say the same thing that I realized.
Doesn't matter.
Doesn't matter.
6 units would be the minimum distance.
That's like
And the point on the paraboloid is the point 112.
at the very beginning, then you say it was 5.
All right, isn't that a nice problem?
Yeah.
And we're done.
A nice,
notes.
nice algebra.
That was half a page. That was 3/4 of the page.
All right, let's look at one more. One more example.
Yes, obviously.
I was just thinking. I was thinking during the quiz. Isn't it amazing that? No, that that because of a car accident, that's the reason that Ben and Shelby are not tardy today. That's kind of amazing, amazing thing.
It's the latest I've been all year, and I'm not.
Right. That's yeah.
How long is this compared to the other one?
Similar.
Similar like.
Example 3.
We want 3 positive integers.
1, 2, 3.
Oh my gosh.
3 positive integers, so that the sum is 32 and x, y squared, z is a maximum. It's similar. So we want 3 positive integers. Well, then the sum would have to be 2018, right? So we want to maximize the product. So
Yeah.
we're maximizing x. We're maximizing f equals x, y squared, z, subject to the constraint that x plus y plus z is 32. So we have a function that we're trying to maximize, but we have this constraint that x plus y plus z has to equal 32. So we're going to solve for z and substitute. So from the constraint, we get that z equals 32 minus x minus y, and our function that we're maximizing, f is x y squared times 32 minus x minus y. I'm going to multiply this out. 32 x y squared minus x squared y squared minus x y cubed. And we want to maximize that. All right, so we're going to take our derivatives. F sub x is 32 y squared minus 2x y squared minus y cubed. And we want that equal to 0. I'm just going to work with one equation at a time this time. So factor out a y squared. Equals 0. Well, what's one thing that would make that 0? Y equals 0, but is that going to maximize the product? No, that would minimize the product. So we're going to ignore y equals 0. So from this piece, we get y equals 32 minus 2x. And we're going to substitute that into what we get for the partial with respect to y. So now we have something to substitute. F sub y is 64 xy minus 2x squared y minus 3xy squared. And that's going to equal 0. I can factor out a y here. I want to substitute for y. I could factor out an x. Well, I'll end up. I'm going to factor the x at the end. 64 x minus 2x squared minus 3xy, and that equals 0. I'm going to substitute. So I get. And I'm gonna ignore y equals 0. I'm gonna ignore y equals 0 again. And we'll ignore x equals 0, but we'll get to that in just a second. So I get 64x minus 2x squared minus 3x times 32 minus 2x, and that equals 0. I can combine like terms and simplify a little bit, and at the end I get 4x times x minus 8 equals 0. We're going to ignore x equals 0, so x equals 8. Y equals 32 minus 16, so y equals 16. And z equals 32 minus 8 minus 16, 8. And our product, x times y times z, or was it xy squared z? Xy squared z is 8 times 16 squared times 8, which is like 20. It's a pretty big number. I don't know what it is. Anybody have a calculator? $16,384. And that's the maximum of that product. All right, questions there? So, I'm not sure why you're so excited for homework, man.
He doesn't do it anymore.
Right, that's what I'm thinking.
Baby.
All right, we're not going to do another example. A couple of things. You can see with constrained optimization, often the algebra is a little bit messy. You might have seen that in your absolute Extrema homework, that some of the algebra is a little bit messy. But I want to talk about an example, something that we've used that comes from what we've just learned. We at least squares lines. Probably half a page, maybe. All right. So with least squares lines, we want to model data with a line. With a line. And the reason it's called the least squares line is because what we do to fit the data is we have a point x1, y1. I'm just going to draw a few points here. x2, y2. Yeah, you use it a lot in stats. x3, y3. And what we're trying to do is fit a line that minimizes the squares of the distances. So that's D1, D2, D3. So we're minimizing the vertical distance from the points to the line. So we fit all this data and we minimize the squares of the distances. There are a lot of ways to fit a line. You can minimize the vertical distance. You can minimize the horizontal distance. You can minimize the perpendicular distance. And all of them give you different kinds of lines that fit. For a least squares line, you usually minimize the square of the vertical distance. So we're minimize the sum of these squares the sum I equals 1 to n for however many data points you have. F of x sub I minus y sub I squared. So we're minimizing the sum of those squares of the distances, those vertical distances. And f of x, we want f of x to be a line. Equals ax plus b for some a and b. So what happens here is s is a function of a and b. So what we do is minimize s with respect to a and b. So s, the sum, is a function of a and b. It's a function of two variables. So what we do is take the partial derivative of that sum with respect to a, set that equal to 0. The partial derivative of that sum with respect to b, which we substitute f of x is axi plus b. Take the partial derivative of that with respect to b. Set those equal to 0 and find the points, find the a's and the b's that make those partial derivatives equal to 0. So that's where the least squares sum, the least squares line comes from, is setting up an equation like this, taking the partial derivative with respect to a, setting it equal to 0, taking the partial derivative with respect to b, setting it equal to 0. So all those equations that they give you in stats class come from taking partial derivatives and finding critical points. Now I just want to write out what you come up with, just to show you how thankful we are that we have calculators. When you do that, so we find the critical points. We get that a is n times the sum I equals 1 to n, x sub I, y sub I, minus the sum I equals 1 to n, x sub I, sum I equals 1 to n, y sub I, over n sum I equals 1 to n, x sub I squared.
Is that second sum and the subtraction of y sub I?
Yes. Minus the sum I equals 1 to n of x sub I quantity squared. That's how you find a. And that comes from taking the partial derivative of that square, sum of the squares, and setting it equal to 0, finding the critical points. B is 1 over n. The sum I equals 1 to n, y sub I minus a. Oh, this is b, sorry. I equals 1 to n, x sub I. That's how we find our least squares line. This is when you plug in your calculator and do linear regression. This is what your calculator's doing.
Is the denominator both the sums of x and y? One.
Yes, they're both x. One is sum of the squares of x sub I, and one is the square of the whole thing. Right, right. And that comes from setting up your sum as a function of a and b, setting the partial derivatives equal to 0, and finding the critical points. So exactly what we've just been talking about. So those formulas that you do in stats, that your calculator does, comes from exactly what we've just been doing.
Mr. Beaver,
Thank goodness we don't have to do this by hand.
aren't quantities the integral? Like
Yes.
area of the integral?
Yes. All right, so it's nice to see, I think it's nice to see something that you learn how to do on your calculator in Algebra 1, that we finally, now in Calc 3, we now know why where it comes from, and if we had to, we could potentially do it by hand. That would be terrible. That would be terrible. Really, it would be terrible. All right. In one of my graduate classes, we did have to do that for the horizontal distance, vertical distance, and perpendicular distance. It was, yeah.
So there's no way that's like a bonus on a test then.
No, it's a huge amount of work.
It's like depending on how many you're doing a lot of calculations, so you're doing that for each point.
Yes.